Okay, so before I start, wanted to get some feedback from you folks about a couple of things. The first is, how are things going? How's the course going? How's the homeworks going? Anything that we can do to make your life simpler, let us know now, or you can post on Piazza. But if you have any thoughts or suggestions, let me know, and I can try to implement them. Hopefully the homeworks are not too time-consuming. That's not the intention, but the hope is that you're using the homeworks to go back and look at the material once again and make sure that you don't have any misconceptions. So that's the main goal of the homeworks more than anything else. And hopefully the projects are going well as well. Any concerns or questions about the course content so far, about the homeworks, about the exams? One of the concerns that was raised on Piazza was that, at least on the midterm, it seemed like the grad students and the undergrads didn't do comparably. I mean, the grad student mean was slightly higher than the undergrad mean. If this continues to the final, we will grade the two separately. In the past, we have not. At least the one time I've taught it, we have not graded the two separately. But we can certainly implement that this time if there is a significant difference. And it looks like there might be. So we'll be watching that closely. Yes, this time's midterm was a little harder than last year's midterm, but not by much. I think the mean this year was maybe 4 to 5 points less than last year. And again, the hope is to not sort of is to not really challenge you on the material, but to just check that you know the stuff. We will be grading on the best of two scales in some sense. So we will be grading you either on the scale that was described on the website, which was an initial indication. If not, and if most of the class does badly, then we will grade on a curve. Last year, we ended up grading, both the sort of scales ended up looking similar. So we ended up grading using the rubric that was described on the website. But if in this case, if the exams end up being harder, we will certainly grade on a curve. So don't fret about that. Again, the hope is to not penalize you as much as just make sure that you're learning the stuff. Okay? So that's the first thing. The second thing is I wanted to get some feedback as to whether the project is going well. There was a post on Piazza about extending the project deadline by a week. But then there was a counter post by someone saying that if the project deadline is extended by a week, some of us would like to continue holding on to the original deadline but get a bonus for that. That is not something we are going to be able to implement. So the question is, would you like the project deadline to be extended, or would you like it to be kept the same? So maybe I'd like to get a straw poll and an initial show of hands for those who would like to keep the project deadline the same versus those who would like to extend it. So let's start with those who would like to keep the deadline the same. So that's 1, 2, just raise your hand up high because I want to count. Okay, so 1, 2, 3, 4, 5. Okay, and the rest, those who want to extend the project deadline, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so, and those who didn't raise either hands for either option, I'm guessing don't care, so that's fine. So looks like you guys want the project deadline to be extended. So we'll take this into account and we'll try to extend it by a week. That's the most we can go without overlapping with the final. Yeah.
Like, the thing is, like, if you extend the project deadline, that means we don't have that much time to, in this sense, study for the midterm.
Yes.
Like, if you look at the calendar, it's going to be the lecture right before the midterm. So my concern with that is it possible to also have project presentations on the original deadline then?
So it's totally fine to have project presentations on the original deadline, but we won't be able to give you a bonus for that because that'll be hard for us to implement.
Yeah, but I just.
So if you want to have.
Present last minute before the midterm.
That's fine. I mean, if you want to stick to an original deadline, I think we can try to implement that. So if the concern is that it's too close to the midterm, you'd rather submit your project stuff up in advance, that's fine with us. We can try to have some slots in the original 2 days as opposed to 1 week delayed. Are there any other concerns about this? So the other announcement is that one of the lectures, I think on the 19th, will be cancelled. So I'm out on a conference. So make sure you don't come to class then. But the rest of the deadlines, at least so far, have stayed the same. We'll push the project deadlines by a week while still keeping the option of some students coming and presenting on the original 2 days. If they so choose to. Okay, so that's totally fine with us, and we'll plan around that. Okay. Any other questions about how the course is going, midterms, exams? The last thing that I wanted to point out is the final will have a cheat sheet. I think it was a 2-page or 1-page 2-side cheat sheet. With the entire course material being part of that, of the final or the second midterm. So it's going to be the entire material, but you have a cheat sheet, so you can refer to that for syntax and stuff that you might have trouble remembering. Okay. So the hope is to, again, not to test you on the syntax as much as test you on the concepts. Okay. Any other questions? All right, so let's get going. So we were talking about B trees last time, and B trees is a mechanism for indexing your data so that you can retrieve it quickly. Okay, so that's the goal of B trees. It's one of the many indexing mechanisms, but certainly, in fact, the most popular indexing mechanism that is implemented pretty much in every single database today. So we talked about how B trees have nodes. It's sort of a hierarchical structure. The internal node maintains some values like 30, 120, and 240, and has pointers to sort of stuff with a range from all values less than 30 up until, but not including 30 on the left-hand side, 30 all the way up until 120 here, 120 to 240 here, and 240 onwards here. Okay, so you can think of these pointers as being to the left of this guy, to the between 30 and 120, to the right of 120 and before 240, and to the right of 240. Okay, so these are how the internal nodes look like. The leaves, on the other hand, have these keys 40, 50, 60, and then the values corresponding to those keys. These are the data records, one corresponding to each key. So you have one corresponding to 40, one to 50, one to 60, and then a pointer to the next leaf. This allows you to skip going up the tree in order to scan the next set of records in sequential order. Okay, so this was the very, very high level idea of what B tree nodes look like. And the other thing to remember was that there's a degree factor D, which is the minimum amount that every node needs to be filled. So this is something that the B tree constantly maintains in order to make it more efficient to retrieve stuff. And at all times you have up to between D to 2D keys in every single node. So 2D is the maximum. If it goes beyond 2D, then you need to do something to reorganize and split it in order to make it once again meet the constraint that it's between D to 2D. Okay, it can't fall below D either. So you need to make sure that this constraint is always met for all nodes apart from the root. And I'll tell you why it's not necessary to maintain it for the root, or it's impossible to maintain it for the root in a little bit. Okay, so again, this is all stuff that we've already covered. I just wanted to give you a quick refresher before we went ahead. So this is an example of a B tree. Root can have one or more filled in keys. The rest have at least D, at most 2D. Okay, in this case, D is equal to 2, and 2D, which is a maximum fill factor in some sense, is 4. So you have 4 slots for each node. In this case, the root has only one key, which is 80. That's totally fine because the root can have 1 or more filled in keys. Rest have to have at least D keys, which is 2 keys. So this node has, for instance, 20 to 60. And if I follow the pointer from the left-hand side of this key, which is 80, I'm going to get stuff, everything up until -infinity to 80. Okay? So that's a range that I'm going to get on the left-hand side. On the right-hand side, I'm going to get everything from 80 onwards. Okay? So that's how I interpret and search this B tree. And then you have more internal nodes. So all of these are internal nodes. And this layer is finally the layer of leaf nodes. Leaf nodes have keys 10, 15, 18 and pointers to the underlying data record. So 10, 15, 18. Okay? And leaf nodes also have a pointer to the next leaf node in sequence, so that if you wanted to read the records in sequence, you don't need to go up the tree. You can just stay at the bottom and then read sequentially by following these pointers. Any questions about this so far? This is just stuff that I covered last time, so I just wanted to give you a quick refresher before I talk about insertions and deletions. All good? Okay. Okay, so let's talk about insertions in B tree. So if I have, once again, let's say that 2D or the max fill factor is 4, I went ahead and inserted yet another, let's say, key pointer into a node. Now my internal node, let's say, has 5 keys and 6 pointers. Because it originally had 4 keys and 5 pointers, now it has 5 keys and 6 pointers. Now I want to split it, right? In order to split it, the way I would do this is to split the pointers in half and then split the keys in half as well. So I'm going to keep P0, P1, P2 on the left-hand side, P3, P4, P5 on the right-hand side. K1 and K2 go into the left-hand side node. K4 and K5 go into the right-hand side. And K3 and a pointer to the right-hand side is going to go to the parent. Okay? So can anyone tell me why I have a pointer to the right-hand side and not to the left-hand side? Yep?
Would you have a pointer to the left side from the original parent node?
Exactly. Yeah, so you have a pointer to the original left-hand side from the parent, and the pointer from K3 to the right-hand side is basically saying that K3 onwards to the next value is on the right-hand side. Okay? So that's why you have a pointer to the right-hand side as opposed to the left-hand side. The pointer to the left-hand side, like he said correctly, is already in the parent node. Okay? Then for the when you have, for instance, an internal node that's a child of let's say the internal node that you're dealing with and you've inserted more stuff that can hold is actually the root. When the root requires a split, then it'll create 2 leaves, both of which now satisfy the constraint of at least D and at most 2D. But the new node that gets created has exactly 1 pointer, which is K3, and the pointer to the right-hand side of this node. Okay? So it's just going to have, actually it's going to have 2 pointers, not just 1 pointer. It's going to have 2 pointers, one to the left-hand side and one to the right-hand side. In this case, in the other cases when you're splitting an internal node, you don't require 2 pointers to be added, you require only 1 pointer to be added. Okay? Let's go through an example to make sure that this is clear. So let's say I have, once again, D is equal to 2, and I wanted to insert key is equal to a record with key 19. So 19 is less than 80, so I'm going to follow this path. 19 is less than 20, so I'm going to follow this path. Finally, I'm at this leaf node. Okay? Now this leaf node has space. for me to add a new record. So I'm going to go ahead and add a key and a pointer to the new record that I was inserting. Okay? So that's how I would insert this guy, the record with key 19, into this tree. Now, what next? So let's say I want to insert 25 after this. Okay? So I follow this path once again because 25 is less than 80. So I'm going to follow this path. Now at this internal node, 25 is between 20 and 60. So it's not less than 20. It's not greater than 60. It's between 20 and 60. So I'm going to follow this path, go down to this node. Now I'm at this leaf node. Okay. So at this leaf node already has 4 slots that are completely filled in. So in some sense, I can't add one more key pointer to that leaf node. So what I need to do now is to split this leaf node into 2 nodes. So I'm going to go ahead and split it. And how would I split it? Well, I would split it into 2. Okay, so I would split it in the middle, and I would split it into 2 such that I have 20 and, sorry, what did I have here? I have 25, 20, 25, 30, 40, 50, right? So these are the new ones, including the new one that was added, which was 25. I have 5 records that I need to reorganize into 2 leaf nodes. So I'm going to go ahead and have the first 2 records with the first leaf node and the remaining 3 records with the next leaf node. So that means I will have 20 and 25 with the first leaf node and 30, 40, 50 with the second leaf node. I could also organize it the other way, but this is a choice that different B-tree implementations can choose to make quite arbitrarily. In this case, we decided to have more stuff on the right-hand side than the left-hand side. That's just our choice. And once I've done that, so I've split this into 2 nodes, 2 leaf nodes, 20 and 25 on the left-hand side, 30, 40, 50 on the right-hand side. I now need to propagate, since I created this new leaf node, I need to propagate the value, the least possible value in this node to the parent. That least possible value is 30. So I now have a pointer from the parent to this node corresponding to 30. Okay? So once again, look at this. Here I had only 20 and 60 at this node. I've decided to split it at 30. So everything from 30, 40, 50 goes to the right-hand side, 20 and 25 goes to the left-hand side, and this value 30 has to go up to the parent because I need to have a way to refer to the right-hand side new leaf node that was created. Okay, so now once I added this value 30 to the parent internal node, I'm now done because I now have a way to refer to the new leaf node which was added. Okay, any questions about this? Any questions about this? Okay, so let's keep going and see what happens. Okay, so let's say I want to delete 30. So once so 30, once again, how do I reach there? I go down this, and then looking at these values, I know that 30 to 60 or 30 to 60 is reachable from this pointer, so I go down this way, and now I'm at the leaf node. I found that I have a record with value 30, so I want to delete it. Okay, so I can go ahead and delete this guy and delete the pointer and shift both of these guys to the left-hand side so that I have the empty space. Okay, so I basically created one empty space in the leaf node. Once I've done that, I can go ahead and change the parent pointer to now refer to 40 instead of 30, okay? Because the smallest value that's reachable from here is actually 40 rather than 30. But even if I leave it as 30, that's not a problem. It's not incorrect. It's still correct because right now I don't have any values between 30 and 40, and so I don't have a decision being made as to where the values from 30 to 40 need to be stored. Okay, so it's totally fine to leave it as 30 if you want to. If you want, you can change it to 40. That's not an important concern. Okay, any questions about this? Yes.
What if you decide to go ahead and insert 30 again?
Okay, so if you decide to go ahead and insert 30 again, you will follow this path and then you would add it to this node if you did not change the value. If you change the value, then you would go ahead and add it to this node, right? Okay, so it doesn't change the correctness of the B tree to either change the value or leave it as it is. It's still correct from the B tree standpoint. Okay, now let's keep going and see what happens as we delete more stuff. So let's say we've gone and deleted this 25 here. So how do we reach 25? We go down the left hand side of this. 25 is between 20 and 30, so I'm going to go down this. Now I've reached the final leaf node from which I want to delete stuff. So let's say I go ahead and delete the key and the value. Unfortunately, now this leaf node has less than D entries. D is 2 in this case, so it has less than D entries, so I need to reorganize. Okay, so I need to reorganize this this tree such that it once again meets my invariant, once again meets my constraint. And how do I do this? Okay, so in this case, what I can easily do is to pull stuff from a neighboring leaf node. In this case, I have noticed that this leaf node, which has 10, 15, 18, and 19, has more than ample keys such that I can grab some of them in order to ensure that this node is once again filled up. Okay, so that is the easiest possible option. If I can grab stuff from either node on the left hand side or the right hand side to ensure that a node is once again filled up, that's what I'm going to do first. Okay, so that's the easiest possible option. We'll talk about what we will do if that can't happen later. So in this case, I'm going to grab stuff from the left hand side. The only value that I need to grab is 19. So I'm going to go ahead and grab 19. And now once again, this leaf is complete. This leaf now has D entries, 2 entries, so we are done. And this leaf also has 2 entries, and we are done, at least from the leaf standpoint. Now, is there something else that we need to do in order to fix this B tree? Anything, any other changes that we need to make? Yep.
Doesn't this 20 need to be changed to 19?
Exactly, right? So the 20 here, unfortunately, is a relic from the old organization and doesn't hold for the new organization, right? So, for instance, this pointer should be taking me to stuff between 20 to 30, except that it's also taking me to 19 in this case, right? So in order to fix that, I need to change this 20 and make it 19, okay? So one point that I skipped over, but I can mention it now, is rotation. This operation is called rotation. Rotation in general can involve either sibling. In this case, we decided to rotate from the left hand side first, and if that didn't work, we would rotate from the right hand side. But you can choose to rotate first from the right hand side and then from the left hand side if you so choose to. It's not a big deal. It's still correct no matter which way you do it. Okay, so in this case, we chose to rotate from the left hand side. Also in this case, it's not possible to rotate from the right hand side because the right hand side has exactly 2 entries, so it can't spare any keys in order to fill this node up. Okay, it can't spare any keys, and therefore the only node that can actually help with this is the left hand side sibling. Okay, all right, so so we are done with this example. Let's keep deleting stuff. So let's say I'm going to go ahead and delete 40 now. Okay, so I'm going to go ahead and delete 40. Once again, how do I get to 40? Go down this. 40 is between 30 to 60, so I'm going to go down this. And now I've reached the leaf node that contains the key 40 and the pointer to the record. and I want to go ahead and delete that. So let's say I go ahead and delete it. Now this leaf node has just one key. It should contain two keys. Okay, it has just one key, but it contains it has just one key. It should contain two keys. Now I need to reorganize. Okay, so the first option that I'm always going to choose first is to do rotation. Okay, so I'm going to try to rotate either from the left hand side or from the right hand side by stealing a key and placing it within my leaf node. Unfortunately, in this case, the left hand side has d is equal to 2, right hand side has d is equal to 2, so both of them barely meet the filling criteria. Okay, barely meet the criteria that at least half of each node must be filled in. And because of that, I can't really do this rotation operation. I can't really steal values from either one of the two siblings, and I now need to do a more costly operation. In this case, the costly operation is to merge nodes. Okay, the costly operation is to merge nodes. So here I can either choose to merge a node from the left hand side or from the right hand side. Here once again I'm making a decision to merge it with the left hand side node. So let's say I decided to merge it with the left hand side node. Now I'm going to get, when I merge these two leaf nodes, I'm now going to have one single leaf node which is going to have 50, a pointer to the record corresponding to 50, and this node disappears. Okay, so this node disappears, but there's still some bookkeeping that I will need to do once I delete this leaf node. What other bookkeeping might I need to do? Yes? You need to delete the 30 key from the top? Absolutely. So you need to get rid of this because this is no longer, this leaf node is being deleted, so this pointer is no longer valid. I can go ahead and delete 30 and the pointer associated with 30, and 60 and the pointer associated with 60 stay as is. Any other bookkeeping I might need to do? Yep.
Just shift 60.
Shift 60, sure. So shift 60 such that it's densely packed once again. That makes sense. What other bookkeeping? Yep.
Update the pointer from the second node.
Right. So right now the pointer from the second node is pointing to stuff that has been deleted, right? So that's not going to help me at all. I need to have the pointer point to the next leaf node in sequence. So I need to have this pointer be updated to this leaf node so that I can once again scan the records in sequence. So that's the last bit of bookkeeping that I need to do. Okay. So once again, I went ahead and deleted, I deleted stuff from parent. Okay, so first is I deleted the leaf node. Second is deleted stuff from parent. And third is I fixed the next pointer. Okay, so these are the three things that I need to do to reorganize the information once I delete a leaf node. Now, unfortunately, the deletions that I make can lead to further deletions up the tree, right? So if I delete, so let's say this node had just 2 pointers, let's say 19 and 30. It didn't have 60, it just had 19 and 30. And I went ahead and deleted 30. Now that means that that node is now doesn't meet the condition anymore. It doesn't meet the condition of having at least 2 keys. So once again, for that node, I will need to steal values from the left-hand side or the right-hand side, try to merge it. If that doesn't work, then try to merge it with one of the left sibling or the right sibling, and then propagate those changes up the tree. Okay, so it doesn't, even though I'm giving you the simplest possible example of deleting and in one step things got fixed, In more complex cases, these changes may need to propagate up the tree, right? So stuff that you delete from the bottom may induce deletions from the top, which may induce deletions from the top and so on, okay? So that's something that you need to watch out for. So you need to constantly maintain at all times this property that every single node has at least 2 keys. Okay, so that's the property that we are constantly trying to maintain. So that's it with B trees. There's a lot more examples, explanation, proofs of correctness, and so on and so forth in the textbook. One small caveat is that they use slightly different notation. What I've opted for is a simple representation where the max fill factor is even 2D, and half of that is what you need to keep filled in at all times. The textbook is a little more complicated and tries to handle both cases of odd and even, so that's something you should watch out for, but it has a lot more examples and a lot more intuition and proofs of correctness and details of algorithms. Okay, so I encourage you to go take a look at the textbook. Don't just leave it at what you see in the lecture. Any questions about this? Okay, so that's it with B trees. Let me move on to hashing. Okay, so hashing is an alternative mechanism for indexing. It's also a useful primitive for some query processing algorithms that we will talk about later. So hash tables, you must have encountered hash tables in your data structures class. Hash tables with the data stored on disk, this is what you would call secondary storage hash tables. Disk is always secondary storage. Memory is primary storage. So secondary storage hash tables are much like main memory ones that you've encountered in your data structures class. So the basics of hash tables are as follows. You have a number of buckets. You have a hash function which takes in a key k and then maps it to 0 to n minus 1 or 1 to n depending on your convention. And you store in bucket corresponding to fk a pointer to the record with key k, right? And sometimes you might have multiple records with key k, so you might have a linked list of those records corresponding to that bucket. Okay, so that's how you would do a hash table in memory. This is stuff that you should be familiar with. So what changes for a secondary storage hash table? So what changes is that here a bucket is a block. So once again, remember that even in the B tree case, we always talked about blocks of stuff that that contain a set of records or a set of tuples. Here a bucket is a block on disk, and you store in bucket fk any record with key k, and you may use overflow blocks if you need to. Okay, so if you have far too many records with a certain hash value f of k, you may use overflow blocks when you need to. So how does that look like? So let's say I have my example with a bucket which corresponds to a block storing 2 records. Okay, so in practice these blocks will contain a lot more records, but this is just for the sake of an example that is easy to convey in class. So here I have a block. Each block contains 2 records. Let's say I have a key corresponding to E, B, F, G, H, A, and C, and the hash value corresponding to E is 0. That means the record corresponding to E is stored in the block corresponding to 0. The hash value corresponding to B and the hash value corresponding to F is 1. Therefore, the records corresponding to B and F are stored in the block corresponding to value 1. The hash value corresponding to G is 2. Therefore, the record corresponding to that is stored in the block corresponding to 2. The hash value of A and C is 3. Therefore, the records are stored in the corresponding block. Okay? Any questions so far? This is fine? Okay. So now what happens when you want to search for stuff? Okay, so let's say I'm searching for the record with key A. I will first compute the hash of A, hash function of A. Let's say that gives me the value 3. I'm then going to go ahead and read the block or the bucket corresponding to 3. I get the records A and C. A is a record that I'm interested in, and so I can return that to the user. Okay, so to do this, this is essentially one disk access. Just go all the way to that block, retrieve that block, give it to the user. Okay, so that's essentially all that needs to be done. It is pretty cheap as opposed to looking at all of the blocks. Okay, so it's much more cheaper than looking at all of the blocks. One slight caveat, which is how do you know where the bucket or the block corresponding to value 3 exists? So in order to do that, you can have a set of pointers in main memory to the buckets for each bucket number. Okay, so or the blocks corresponding to each bucket number. Right? So main memory will have pointers. So one way to visualize this is to think of there being in main memory for value 0, 1, 2, 3, and so on, you have pointers to where the block is on disk. Okay, so in order to look up which block I should read once I've computed the hash function is given value 3. I will look up my array in main memory. I will find that the block that I'm interested in is in this location on disk. So I will go ahead and read this block and then find all of the records that match. In this case, the only record that matches is A. Okay? Questions? All right. So insertion on a hash table into a hash table, a regular hash table, is pretty straightforward. If you have space in your block, then you can go ahead and add stuff. So let's say your hash value of D is 2, and D hasn't yet been added. I can go ahead and add it if there's space. And if there's no space, I can create an overflow block. So let's say the hash value of key K is 1. The block corresponding to that is already full. It contains B and F. I can create a pointer to an overflow block which will now contain K and any other records that I choose to insert that also have hash value corresponding to 1. Okay? So once this gets filled up, I may have another pointer to yet another like overflow block, and once again that might have yet another pointer to yet another overflow block, and so on. Okay? So if there are no overflow blocks, then this type of hash table, this vanilla hash table, is actually really good. Okay? You only need to look up one block to find the record that you care about. So you hash the value that you care about, the key that you care about. You go to that block, you retrieve all of the records in that block, and you're done. Okay, so if there's no overflow, this is actually a really good option. The unfortunate thing is that if there are many overflows, then you may end up having a long chain of blocks that you need to retrieve for those keys that have a large number of records, or those hash values that have a large number of records. So if there are a large number of overflow blocks, then the performance is pretty bad for this vanilla hash table scheme. Okay? Because it's no longer restricted to one disk access, you may need to do many disk accesses in order to retrieve your records. Okay? So that's the downside of this approach, which is that the performance degrades very quickly if you have a lot of overflow blocks. So how do we fix this issue? The way to fix this issue is to have a hash table that dynamically grows as more and more stuff is added to it. Okay? while all of the while ensuring that you are always looking up one block to find the records that you care about. Okay? So that's the constraint that the new type of hash table that I'm going to describe is trying to maintain. You're always trying to ensure that you're returning one block to a user, and at the same time you will allow your hash table to grow in order to maintain this constraint. So let's say, so this form of hashing is called extensible hashing because it extends the size of the hash table dynamically. So this hash table has a hash function h, which returns numbers in 0 to 2 to the power k minus 1. And at the start, you don't use all of the k bits, you use much fewer bits, and you dynamically decide to use more bits as more and more data is added. Okay, so that's the dynamic nature of this hash table. So you'll start by using just 1 bit, and then you'll extend to 2 bits, and then you'll extend to 3 bits, only if you absolutely need to. The other emphasis, which is really cool, is that you have this notion of shared blocks, blocks that are shared across different buckets. So you only instantiate new blocks when you actually need to. You don't instantiate new blocks every single time. So unlike the hash table that we talked about earlier, the vanilla hash table where you have a block corresponding to every single bucket, here you don't need to have a block corresponding to every single bucket. Multiple buckets can point to the same block. Okay? So let me show you an example and that will become clear. So there are two numbers to keep in mind here. The first number is the maximum number of bits in your hash function. So remember I talked about having a hash function that returns numbers between 0 to 2 to the k minus 1. So your k, which is the maximum number of bits that you have, in this case is 4. Okay, so that's the maximum number of values that you can use for indexing. The second number that is relevant for this hash table is the number of buckets that you have at any given point. In this case, I is equal to 1. This is the number of bits that are relevant to create buckets. So because I is equal to 1, you have two buckets, one corresponding to 0 and one corresponding to 1. And once again, a block can only have 2 records. This is the same constraint that we saw earlier. Okay, so when you start, let's say I have just 2 records, one corresponding to key 0, 0 or hash value 0, 0, 1, 0, and another corresponding to hash value 1, 0, 1, 1. Here, since I'm only looking at 1 bit, the first bit, I'm only looking at the first value of this hash function, and therefore this record with 0, 0, 1, 0 is placed in this block, and this record with 1, 0, 1, 1 is placed in this block. Okay? So right now the buckets are only looking at the first bit of your hash value. The hash value is 4 bits, but you are only looking at the first value, first bit. Okay. Now, the second thing to notice here is that these blocks have a bit counter which records the number of bits that are relevant for that block. Okay. So in this case, at the start, the bit counter is set to 1 because only 1 bit is referred to in determining membership in this block. And in order to indicate that only 1 bit is referred to, I have this notation which is 0, 1, 0, even though the overall hash function value is 0, 0, 1, 0. I'm using the parentheses to indicate that these values are not important for determining membership in this block. Okay? Okay, so far so good. This is the starting point. Let's see what happens when we add stuff. So I went ahead and decided to insert 1, 1, 1, 0. My buckets are indexed based on the first bit. So I'm going to look at the first bit here. The first bit is 1. So I'm going to look at the block corresponding to 1, that is this guy. this block has free space, so this was not filled in, and so I'm going to go ahead and fill in this 1 1 1 0 into this slot. Okay. Once again, the convention is that I'm only looking at the first bit, and therefore I'm indicating that as, sorry, okay, let me just cancel it. So I'm only looking at the first bit, and I'm indicating that as 1 1 1 0. This is just to show that I'm only looking at the first bit to determine membership in that block. Okay. Any questions so far? I'll tell you why the bit counter and these parentheses make sense in a couple of slides, but anything that's not clear about what I've explained so far, let me know. Any questions about this? Okay, so let's keep going and see what happens. Okay, so right now I had a slot, I filled it in, all is good. Okay, what happens if I wanted to insert something else? So I went ahead and said, hey, I want to insert 1 0 1 0. Unfortunately, I don't have space to add 1 0 1 0 to this block. Because I don't have space to add 1 0 1 0 to this block, I need to go ahead and split this block into 2 and also simultaneously extend the bucket array. Okay, so this happens in 2 steps. The first step is to extend the set of buckets. So right now you had buckets corresponding to 0 and 1. Now the buckets are going to correspond to 0 0 0 1 1 0 and 1 1. Okay, and I, which was 1, is now going to become I is equal to 2. Okay, because 1 bit was not sufficient in order to maintain all of these records, so I need to increase it to 2 bits. Okay, so now I have 2 bits in order to sort of index the buckets. So I have now 2 bits, and so I have the 4 values 0 0 0 1 1 0 and 1 1. The 0 0 and 0 1, now both of them point to the same block in the past, which was the 0 0 1 0 block, right? So this same block that was there in the past, both of them point to this because they both have the first value as 0. Because they both have the first value as 0, they both point to the same old data block that we had in the past. Similarly, both of these values 1 0 and 1 1 point to the same data block which corresponded to the 1 block in the past. Okay, so notice that the 1 block will now contain values corresponding to, or will now correspond to the values. Let me try to state that again. So you had 2 blocks in the past, 1 corresponding to 0, 1 corresponding to 1. Now the block corresponding to 1 will be pointed to by 1 0 and 1 1, and the block corresponding to 0 will be pointed to by 0 0 and 0 1. Okay, so that's what is happening here. I just doubled the buckets but maintained the same set of blocks. Okay, nothing else has changed so far. All that I've done is double the buckets. So double the buckets, the data blocks stay the same. Is it clear so far? Okay. So now I still haven't inserted what I wanted to insert, right? So I still haven't inserted what I wanted to insert. So what I'm going to do now is to go ahead and insert the 1 0 1 0 value, right? So I want to insert 1 0 1 0. In order to insert 1 0 1 0, I'll follow this pointer corresponding to 1 0. I'll try to insert 1 0 1 0 here. That doesn't work, and therefore I need to split this block. In this case, I can split this block because this block is only referring to one of the bits, not both of the bits. If it was referring to both of the bits, I can't split that block. But it's only referring to one of the bits, therefore I can split it. And because it's referring to only one of the bits, I can split that increment the counter of the number of bits that it's referring to 2, I can now have pointers, one corresponding to 10 and one corresponding to 11, that is split away and point to two separate blocks, two separate data blocks. Okay, so all the while this block corresponding to 00 and 01 stays the same. It's not changed, it still corresponds to one bit that is relevant for determining membership of that block. Okay? Yes?
But the data block size has to be 2. It cannot be extended to like 4 or something.
The data block size is a constant. That's something that we are keeping fixed. You can certainly have data block size as 4 as the initial constraint, and so you can add more stuff if you want to, if that was the initial constraint. In this case, for this example, it's fixed as 2. So now, once I've incremented this counter, which is the bit counter for a block to 2, now the bit counter matches the count corresponding to I, which is the number of buckets. So if I went ahead and added more stuff or tried to add more stuff to this block, then I won't be allowed to, because I can't split that block into 2 anymore, because I, which is the number of bits that I'm using to index the buckets, matches the bit counter. Okay, so once again I'm going to have to split the buckets. Okay, once again I'm going to have to double the number of buckets or split the buckets into 2 in order to make that change happen. On the other hand, if I wanted to add a new entry to this block, the block which has a free slot, I can freely go ahead and add it. If I wanted to add one entry into this free block, I can freely go ahead and add it. If I wanted to add multiple entries to this block, I can still go ahead and do it, because I have a bit counter which is less than 2. Okay, I can, once I hit my constraint where it's filled up, I will need to split it into 2, and then the pointers corresponding to 00 and 01 will point to 2 separate blocks, such that everything which starts with 00 will be stored in one block, everything that starts with 01 will be stored in another block. Okay? So I hope I have an example with that, but let me see if I do or not. Okay. So let's say, so this is what we had earlier, right? So we had these 2 data blocks with bit counter is equal to 2, and this data block with bit counter equal to 1. My I was equal to 2. Let's say I have, I insert 0, 0, 0, 0. That's easy. I have space. So I'll follow this. I'll get to this block, and then I can go ahead and add 0, 0, 0, 0 to this block. I have space, so I'm done. Okay, now let's try to add 0, 1, 0, 1. So I will follow this pointer, go to this block. I find that this block is filled up, so I can't reuse this block, right? So I need to do some reorganization. I then go and look at this bit counter. I notice that this bit counter is 1, even though I is 2. So what I can do is to split this into 2 blocks. So I have one block here and a second block here. And let's say this block corresponds to 0, 0, and this block will correspond to 0, 1. Let me write it somewhere else. So this block will correspond to 0, 0, this block will correspond to 0, 1, and I had 0, 0, 0, 0 here. I now have space for 0, 1, 0, 1 in this, so I will add 0, 1, 0, 1 here. I'm going to change the bit counter here to 2, because it now requires 2 bits to determine membership here. Change the bit counter for this guy to 2, and change the pointer for this guy to 0, 1. So this gets deleted, and now this is my new organization. Okay? Now, if I went ahead and added yet another thing with starting 0, 0, so let's say I wanted to add 0, 0, 0, 1, then I will try to add it to this block, but this block is filled up. And because it's filled up, and the fact that the bit counter matches I can't really do anything more with it. and therefore I will need to double the number of buckets. Okay, so I will have a set of buckets corresponding to 0, 0, 0, 0, 0, 1, and so on up until 1, 1, 1. Okay? Any questions about this? So one thing to remember here, at least the higher level, is that you have you start with a small number of blocks, and you may have more buckets that point to a smaller number of blocks. You will expand the blocks out as you need to. Okay, so where there's a lot of activity, there's a lot of key values, you may split the blocks up until you meet your constraint that the bit counter is equal to I. If you hit that constraint, then you may need to reorganize the number of buckets, but up until that point you will split the number of blocks. If not, if you have a large number if you have a small number of records, you can compactly store that in fewer blocks by having multiple buckets point to the same block, right? So we saw that here. So we had two buckets, one corresponding to 0, 0 and one corresponding to 0, 1, point to one single data block here, which allowed us to not have to store multiple data blocks when it's not needed. This data block only had one record, right? So since you had only one record, why should you be storing two separate data blocks, one corresponding to 0, 0, one corresponding to 0, 1, when only one is necessary? The second thing to note here is that at all cases, whenever you're following a pointer from any value, you will get to one block. There's no multiple blocks. It's always one block, right? So that's another nice property of this structure, which is that you are always going to return at most one block corresponding to your key. Okay? So that's another good thing as compared to the linear hashing. But there are some downsides as well, and that's hopefully what I'm going to be talking about. Okay, so turns out, okay, so I guess I have a question, so let's work through that as well. So let's say I went ahead and did what I was supposed to here. So I'll work through that once again. So I had 0, 0, 0, 0 followed by 0, 1, 0, 1. I went ahead and added 0, 0, 0, 0, and I'm trying to add 0, 1, 0, 1, but that doesn't fit, so I need to split the block here, but not the bucket array. The bucket array can stay as is because my bit counter is still less than 2. So I've split that, and now I have 0, 1, 0, 1 in the second block, and 0, 0, 1, 0 and 0, 0, 0, 0 in the first block. Okay, and the bit counters for all of the blocks now is 2. Let's say I want to insert 1, 0, 0, 0. What would I need to do now? Any suggestions? Extend the bucket array, right? So correct. So let's see what happens. So let me keep the data blocks as is. I'm just going to extend the bucket array. Okay, so I have now these 8 buckets. Where are these guys going to point to? Where would this guy point to of these 4 data blocks? The first one? Right. What about this guy? Also the first one, right? Similarly, these two would both point to this guy. And these two would both point to this guy. And these two would point to this guy. Okay, so now you have, in some sense, double the buckets, you've not done anything with the blocks. Now you can once again try to insert stuff into the blocks. So you now try to insert stuff into the block corresponding to 1010. Let's follow that. So you have a key value corresponding to 100. You're going to follow the pointer here, and you now have a bucket corresponding to 1000. Now that bucket is full, but the bit counter is less than 3, right? The bit counter is 2, it's not 3. So I can go ahead and try to split that. So I'm going to split this. So I'm going to replace this guy with 2 blocks. I'm going to write them here because it's getting really messy down there. So I have 1 block here, 1 block here. And both of them are going to have the bit counter set to 3, right? And the first of these 2 is going to contain values corresponding to 100. The second one is going to contain values corresponding to 101, right? So I have 1 0 0 0 in the first block and 1 0 1 1 in the second block and 1 0 1 0 in the second block. Okay, so you had these 2 to begin with, and you also had 1000, so you have these 3 values that need to be reorganized into these 2 blocks. So that's how you do it. Is any of this not clear? Let me know now. So it's helpful to think about you having 2 possible operations. One operation is doubling the buckets. The second operation is splitting a block into 2. Either one of those 2 can be helpful while you're doing insertion, right? So the first strategy is to try to split the block into 2 if your bit counter is less than I. If that doesn't work, then you have to split the buckets. Once you've split the buckets, then you can go back and retry to insert it into the block. And if that doesn't work, then you go back and split again. And you keep doing this up until you can actually insert the records. Okay? Yes?
Just a question. For 0, 1, 1 in the bucket, is it pointing to still the up, or?
It's pointing to this guy. Sorry, I don't know. Both of these are pointing to the same block. So I didn't mean to point it to the middle of that block. I meant to point it to the start of the block. Yes?
Can you further split the buckets?
Which buckets?
I mean, like you split it, like at first it was like 2 days.
Yeah.
And then you split it into like 3 days. And because we set the I equals to 4.
Yeah.
So
You can split it up to 4, right? You have up to 4 bits in your hash value, and therefore you can split it up to 16 entries. You can't go beyond that because your hash value doesn't have stuff beyond that. So that's another limitation. So you need to select your hash function such that it's fairly long enough, such that you can keep splitting as many times as you need to. Yes?
Why would you not just initially use like the maximum amount of hash bits?
Okay.
Instead of like expanding the table?
Absolutely. So why would you choose to not use the maximum number of hash bits for the buckets or for the data blocks? Which part are you not?
The buckets.
Okay. So for the data blocks, let me explain why it makes sense to have the data blocks, and then I'll come to the buckets. For the data blocks, it makes sense to have as few data blocks as possible. That's essentially what this scheme is helping you do. For the buckets, the reason why we don't go ahead and use the entire width right off the bat is because you may not need to, and because memory is expensive. So these pointers are maintained in memory, and you don't want to do that. You don't want to initialize to your maximum possible capacity until you absolutely need to. That's why, in some sense, you do it dynamically. This does mean that you're paying a penalty every time you're doing a doubling, but that's a cost that we're willing to take because it is still keeping the pointers that are stored in memory as small as you absolutely need to. Anything else? Okay. So let's talk about performance briefly. The good thing about extensible hash tables is that there are no overflow blocks. Access is essentially always one read for distinct keys if you have a collection of distinct keys. So you just need to look at one block if you wanted to retrieve stuff, so that's nice. But at the same time, extensions are disruptive and costly, right? So after an extension, so firstly they are costly and disruptive because you're doubling the number of buckets, and that's expensive. Also, after an extension, the bucket table may no longer fit in memory. Okay, so there may be cases where you have your I is as high as, let's say, 15 or something, and you no longer have the width, you no longer have the capacity in main memory to store all of those pointers. That makes it even more expensive because you may have to store those pointers on disk, retrieve them on demand. That's not fun. Okay, so after multiple extensions, these bucket tables may no longer fit in memory. That is a problem. There are also worst case scenarios that are really, really bad. So let's say you had, once again, your block containing 2 records, and let's say I have 3 records whose keys share the first 20 bits. If you have 3 records whose keys share the first 20 bits, you are essentially going to keep on doubling up until you hit I is equal to 20. There is no way you can store it with fewer bits than I is equal to 20. So you're going to have to keep doubling the bucket array because there is no way your blocks can hold more than 2 records. Okay, so these 3 records can't be in the same block if you're assuming 2 records per block, but a block split would require setting I is equal to 20. Okay, so you essentially need to accommodate for 1 million buckets, even though in this case there are only 3 records. Okay, so there are worst case scenarios that can be really, really bad for the extensible hash table. Okay, so the next scheme that we are going to talk about is trying to do a little bit of both. It's trying to reduce the costly effects of extensions, but at the same time sort of relaxing a little bit that access is always one read. Okay, so it might relax that a little bit, so it might lead to overflows in some cases, but that is at the benefit of not having to do extensions. So let's talk about that very, very briefly, or maybe I shouldn't, maybe I won't. I'll cover this on Wednesday. Okay, so the next scheme that I'm going to talk about is a linear hash table. It's not going to double at every step. It's going to step 1 bucket at a time and going to deal with some of these issues. So it's sort of like the best of both worlds, if you will. Any questions about any of this stuff? Okay, I'll see you on Wednesday. So one last note, if you have any further grievances with extending the project deadline by a week, let us know on Piazza, but the majority opinion is that we're going to extend it with slots on the original 2 days if you really want to present beforehand. Okay, so we'll go ahead and make that announcement soon.